July 3rd, 1938. Stoke Bank, Lincolnshire, England. The needle on the dynamometer car's speedometer climbed past numbers that seasoned railway engineers insisted were impossible for steam traction. At 125 miles per hour, the instrument trembled violently as LNER locomotive 4468 Mallard thundered down the gradient with a force that defied everything traditional steam engineering claimed was achievable. Driver Joseph Duddington felt the footplate shudder beneath him as speed increased beyond any previous steam locomotive performance. His hand steady on the regulator, he watched the countryside blur into streaks of green and brown. Behind him, fireman Thomas Bray maintained steam pressure through continuous shoveling, feeding Welsh coal into the firebox at a rate that would have exhausted most men within minutes. In the dynamometer car, Inspector Sam Jenkins watched instruments record data that would either validate 4 years of controversial design decisions or confirm critics' predictions that streamlined locomotives represented dangerous engineering fantasy. The speedometer needle pushed past 126 miles per hour at exactly 5:27 p.m., marking a moment that traditional locomotive engineers had declared physically impossible for steam traction. British railway engineering in 1938 operated under assumptions that had governed steam locomotive design since George Stephenson's rocket proved the concept in 1829. Weight distribution, boiler pressure, valve gear complexity, and mechanical friction created natural speed limits that competent engineers accepted as unchangeable physical laws. Steam locomotives pulled trains. They didn't break speed records that required abandoning proven design principles. Sir Nigel Gresley's streamlined designs had faced ridicule from the moment the first A4 Pacific emerged from Doncaster Works in September 1935. The wedge-shaped nose, covered wheels, and aerodynamic casing violated aesthetic sensibilities that associated proper locomotives with exposed machinery and traditional proportions. Engineering committees questioned whether the streamlining served any functional purpose beyond marketing gimmicks aimed at passengers who didn't understand railway mechanics. The London and Northeastern Railway's investment in high-speed passenger service seemed financially reckless to competitors who prioritized freight revenue and operational reliability over passenger comfort. Why risk experimental technology when proven designs delivered consistent performance? The Great Western Railway's conventional locomotives hauled express services profitably, without aerodynamic modifications or high-pressure boilers that complicated maintenance. As Mallard's speed exceeded 126 miles per hour that July afternoon, the middle big end bearing began overheating from sustained maximum performance. White metal lubricant liquefied under pressure that no locomotive bearing had previously experienced during regular operation. The damage would require immediate repair work, validating critics who predicted that extreme speed attempts would destroy mechanical components designed for sustainable service rather than record-breaking stunts. But the speedometer reading stood undisputed at 126 miles per hour, a world record for steam traction that would never be exceeded. Mallard had achieved what traditional engineers insisted was impossible, transforming skepticism about streamlined design into recognition that British railway engineering had fundamentally reimagined what steam locomotives could accomplish. British steam locomotive development in the early 1930s reflected engineering conservatism that prioritized incremental improvements over revolutionary redesign. The Great Western Railway's Castle and King-class locomotives represented the pinnacle of conventional thinking. Large boilers, moderate steam pressure, traditional valve gear, and exposed mechanical components that allowed easy maintenance access. Railway mechanical engineers treated aerodynamics as irrelevant to locomotive performance. Trains operated at speeds where air resistance represented minimal energy loss compared to rolling friction and grade resistance. The railway executives' technical committees dismissed streamlining as aesthetic decoration that added weight and construction costs without meaningful performance benefits. Locomotive weight distribution followed principles established decades earlier. Heavy boilers positioned over driving wheels maximized traction, while exposed running gear allowed maintenance crews to inspect bearings and valve mechanisms without removing protective casings. Any design that prioritized appearance over mechanical accessibility violated fundamental maintenance requirements that kept locomotives operational. Steam pressure limitations reflected metallurgical constraints and safety regulations. Boilers operating above 250 pounds per square inch required specialized steel alloys and welding techniques that increased construction costs while introducing potential failure points. Conservative engineers argued that moderate pressure with larger cylinder volumes delivered equivalent power more reliably than high-pressure systems that stressed materials beyond proven performance thresholds. The London Midland and Scottish Railways approach exemplified industry consensus. Sir William Stanier's Princess Coronation class locomotives used conventional designs scaled to larger dimensions. When marketing departments requested streamlined casings for publicity purposes, engineering departments complied reluctantly, viewing the modifications as cosmetic additions that complicated maintenance without improving operational performance. Valve gear complexity represented another constraint that limited speed potential. Traditional Stephenson valve gear operated reliably at conventional speeds but created mechanical harmonics at higher velocities. The oscillating components that distributed steam, too. Cylinders experienced resonance frequencies that reduced efficiency and increased wear rates when locomotives exceeded design speed parameters. European railway engineering faced similar philosophical constraints despite Continental Railway's emphasis on passenger service. German State Railways Class 05 locomotives achieved 124.5 miles per hour in May 1936, but the specialized three-cylinder design required maintenance complexity that prevented widespread adoption. The speed record validated experimental engineering, but didn't challenge fundamental assumptions about practical locomotive design. Sir Nigel Gresley's position as Chief Mechanical Engineer of the London and North Eastern Railway gave him authority to pursue experimental designs, but his reputation depended on operational success rather than theoretical innovation. The LNER's financial struggles during the Depression made costly experiments particularly risky. Shareholders questioned investments in high-speed passenger service when freight operations generated more reliable revenue. The technical committees reviewing Gresley's streamlined proposals identified numerous practical concerns. Enclosed running gear prevented visual inspection of bearing temperatures and lubrication systems. Aerodynamic casings added weight that reduced efficiency. High-pressure boilers required specialized maintenance procedures that increased operational costs. The entire concept seemed to prioritize publicity over engineering substance. Yet Gresley persisted with specifications that defied conservative wisdom. Wedge-shaped nose, fully streamlined body, Kyle-Chap double exhaust system, 250 pounds per square inch boiler pressure, and internal valve gear modifications that allowed sustained high-speed operation. Critics viewed the combination as engineering recklessness that would produce spectacular failures rather than reliable express locomotives. The first A4 Pacific, Silverlink, emerged from Doncaster Works in September 1935 to reactions ranging from incredulity to open ridicule. Railway Engineering magazine published editorials questioning whether streamlined casings served any purpose beyond marketing theater. The locomotive's appearance violated aesthetic conventions that associated proper railway engineering with visible mechanical components and traditional proportions. Maintenance engineers immediately identified practical concerns. The streamlined casing prevented visual inspection of motion work during operation, making it impossible to detect bearing overheating or lubrication failures until damage occurred. Traditional locomotives allowed crews to observe running gear continuously, identifying problems before mechanical breakdowns stranded trains between stations. The Great Western Railway's engineering staff dismissed streamlining as unnecessary complication. Their Castle-class locomotives hauled express services reliably using proven designs that prioritized maintenance accessibility and operational simplicity. Why adopt experimental technology when conventional engineering delivered consistent performance without introducing unknown failure modes? Critics focused particular skepticism on the Kyle-Chap exhaust system's double chimney arrangement. Traditional single blast pipes had evacuated cylinder exhaust for a century without requiring complex double exhaust systems. The modification added manufacturing costs and maintenance complexity while making unproven claims about improved steaming efficiency. The Railway Gazette published detailed analysis concluding that streamlining benefits remained unproven at speeds British railways actually operated. Wind tunnel testing suggested aerodynamic improvements became significant only above 90 miles per hour, speeds that express services rarely sustained for extended periods. The weight penalty from streamlined casings potentially canceled any aerodynamic advantages during normal operations. Firemen's unions raised safety concerns about the enclosed cab design. Traditional locomotives provided clear sight lines for crews monitoring track conditions and signals. The A4's streamlined nose restricted forward visibility, forcing drivers to lean out of side windows to see approaching signals clearly. Critics argued that aesthetic considerations had compromised operational safety. The high-pressure boiler specifications generated particular controversy. Boilers operating at 250 pounds per square inch required careful water treatment and vigilant maintenance to prevent scale buildup that could cause catastrophic failures. The Railway Inspectorate's safety reviews questioned whether the pressure increase justified the additional operational risks and maintenance requirements. Mechanical engineers noted that the A4's valve gear modifications, particularly the increased valve travel necessary for high-speed operation, increased wear rates and required more frequent maintenance intervals. Traditional valve gear lasted years between overhauls, but the A4's specifications suggested shorter operational periods between major repairs. Cost analysis reinforced skepticism. Each A4 locomotive cost approximately £8,000 compared to $6,500 for conventional Pacific designs. The 23% premium bought unproven streamlining and experimental systems rather than additional locomotives using reliable technology. During the Depression, when railway companies face severe financial constraints, experimental expenses seemed particularly irresponsible. Competitors viewed the A4 program as publicity stunt aimed at passengers rather than serious engineering advancement. The London Midland and Scottish Railway's Princess Coronation class achieved comparable speed performance using conventional designs with cosmetic streamlining added afterward. This approach preserved maintenance accessibility while satisfying marketing departments' desires for modern-looking locomotives. When Silverlink completed trial runs in September 1935, reaching 112.5 miles per hour during testing, critics attributed the performance to favorable track conditions and temporary boiler performance rather than fundamental design advantages. Sustained operational service would reveal whether streamlined complications delivered genuine benefits or merely created maintenance headaches. The A4's revolutionary performance emerged from systematic engineering solutions that addressed specific limitations in conventional steam locomotive design. Each innovation built upon theoretical understanding of thermodynamics, aerodynamics, and mechanical dynamics that traditional approaches had ignored or dismissed as impractical. The Keelchap double exhaust system represented the most significant advancement in steam locomotive efficiency since the adoption of superheating. Designed by Finnish engineer Kyösti Kilala and French engineer André Chapelon, the system created a more effective vacuum in the smoke box through precisely calculated exhaust geometry. The double blast pipe arrangement produced stronger draft that improved combustion efficiency while reducing back pressure on cylinder exhaust strokes. Traditional single blast pipes created turbulent exhaust flow that wasted energy and limited steaming capacity. The Keelchap system's careful aerodynamic design smoothed exhaust flow through the smoke box, allowing the boiler to generate steam more efficiently at high power outputs. Testing demonstrated 8 to 12% improvement in thermal efficiency compared to conventional blast pipe arrangements, translating directly into fuel savings and sustained high-speed capability. Internal streamlining of steam passages eliminated flow restrictions that limited power output in conventional designs. Traditional locomotives featured steam pipes with sharp bends and abrupt diameter changes that created pressure drops and turbulence. The A4's carefully designed steam circuits maintained consistent flow velocities from boiler to cylinders, reducing energy losses and allowing more effective use of available steam pressure. The wedge-shaped front end wasn't merely aesthetic. Computational analysis and wind tunnel testing demonstrated significant reduction in air resistance at speeds above 75 miles per hour. The smooth nose profile created laminar airflow over the boiler casing, reducing turbulent wake formation that created drag in conventional locomotives. At 100 miles per hour, aerodynamic improvements saved approximately 180 horsepower compared to traditional designs. Wheel fairings that covered the driving wheels and motion work served functional purposes beyond appearance. The enclosures reduced turbulent airflow around rotating components that created significant drag at high speeds. Additionally, the fairings protected bearings and motion work from track ballast impacts that could cause damage during high-speed operation. The valve gear modifications incorporated lessons from extensive testing at Vitry-sur-Seine in France, where André Chapelon had pioneered advanced steam locomotive thermodynamics. Increased valve travel and modified timing allowed more complete expansion of steam in the cylinders, extracting more energy from each pound of steam generated. The modifications required precise manufacturing tolerances but delivered measurable efficiency improvements. Boiler design incorporated innovations that increased steam generation capacity without proportional weight increases. The combustion chamber extension increased heating surface area, while improved circulation patterns ensured more uniform heat transfer. The 250 pounds per square inch working pressure, higher than most British locomotives, provided more energy per pound of steam, allowing smaller cylinders that reduced reciprocating mass and improved mechanical balance at high speeds. The conjugated valve gear for the inside cylinder, operated through a complex linkage rather than separate valve gear, reduced weight and mechanical complexity. Traditional three-cylinder locomotives required 3 complete valve gear mechanisms. Gressley's conjugated system eliminated one set of valve gear, reducing reciprocating mass and improving dynamic balance during high-speed operation. Roller bearings on the leading and trailing trucks reduced friction and improved high-speed stability. Traditional plain bearings required constant lubrication and generated significant heat at high speeds. The roller bearings provided lower friction with less maintenance, allowing sustained high-speed operation without bearing failures that plagued conventional designs. Careful attention to dynamic balancing eliminated vibration issues that limited other locomotives' speed capabilities. The A4's reciprocating masses were precisely balanced to minimize track forces and reduce wear on both locomotive and permanent way. This attention to balance allowed sustained speeds that would have caused excessive track damage or mechanical failures in less carefully balanced designs. Silverlink's inaugural run on September 27, 1935, transformed skepticism into cautious recognition when the locomotive hauled the Silver Jubilee Express at sustained speeds above 90 miles per hour. The 232-mile journey from London to Newcastle averaged 8 miles per hour, including all intermediate stops, demonstrating that streamlined design delivered operational advantages beyond theoretical projections. The 4-hour schedule for the Silver Jubilee service required sustained speeds of 90 miles per hour on favorable sections, performance levels that conventional locomotives could achieve only temporarily. Silverlink maintained high speeds effortlessly, with firemen reporting easier steaming and lower coal consumption than expected for such demanding schedules. Dynamometer car testing provided quantifiable data that validated design innovations. At 90 miles per hour, the A4 consumed 15% less coal than conventional Pacifics operating at equivalent power outputs. The aerodynamic improvements and thermodynamic efficiency translated directly into operational cost savings that justified the initial construction premium. Maintenance records from the first year of service contradicted critics' predictions about streamlined complications. Despite initial concerns about inspecting enclosed running gear, maintenance crews developed efficient procedures for removing access panels. The actual maintenance time proved comparable to conventional locomotives, while bearing temperatures remained lower than traditional designs due to improved lubrication protection from track debris. The public response exceeded all marketing projections. Passengers specifically requested tickets on the Silver Jubilee service, paying premium fares to experience high-speed streamlined travel. The locomotive's distinctive appearance and smooth high-speed performance created publicity value that extended far beyond railway enthusiast circles. Competitor railways took notice. The London Midland and Scottish Railway accelerated development of their streamlined Princess Coronation class after witnessing the Silver Jubilee's commercial success. Even skeptical Great Western Railway engineers acknowledged that passenger demand for high-speed service represented genuine market opportunity rather than temporary publicity fascination. By early 1936, 3 additional A4 locomotives had entered service, each incorporating minor refinements based on Silverlink's operational experience. The production series demonstrated that streamlined design could be manufactured consistently while maintaining quality standards. The locomotive's reliability contradicted warnings that experimental technology would produce maintenance nightmares. Speed testing on March 5, 1936 saw Silver Link reach 113 miles per hour during trial runs, establishing British speed records that conventional locomotives couldn't match. The performance validated calculations suggesting that aerodynamic improvements became increasingly significant at speeds above 100 miles per hour. Financial analysis demonstrated unexpected economic benefits. The Silver Jubilee service generated 30% higher revenue per train mile than conventional express services, with passengers willing to pay premium fares for guaranteed high-speed travel. The additional revenue stream justified the A4's construction costs within the first year of operation, contradicting predictions that streamlined locomotives represented uneconomic engineering indulgence. Photographic evidence showed the A4's distinctive appearance created marketing value beyond traditional railway advertising. Newspapers published feature stories about the streamlined expresses, generating publicity that attracted passengers who had never previously considered long-distance rail travel. The locomotive's aesthetic appeal became a commercial asset rather than merely an engineering characteristic. By the time Mallard entered service in March 1938, the A4 class had accumulated operational experience that refined understanding of high-speed steam locomotive capabilities. 28 additional units had been constructed or were on order, representing the LNER's commitment to streamlined express service as core business strategy rather than experimental program. Critics who had dismissed streamlining as publicity stunt faced mounting evidence that aerodynamic design delivered measurable performance advantages. The A4's operational success transformed industry assumptions about practical speed limits for steam traction, establishing new benchmarks that conventional designs couldn't achieve. Mallard's selection for the world speed record attempt reflected specific technical characteristics that distinguished it from other A4 locomotives. The installation of a coil-chap double exhaust system during construction provided superior steaming capacity compared to earlier units. The locomotive's mechanical condition in July 1938, with all bearings recently serviced and valve gear precisely adjusted, offered optimal circumstances for maximum performance testing. The route selection demonstrated careful engineering planning. Stokebank's 4-mile descent from Grantham provided a 1 in 200 gradient that allowed gravitational assistance while maintaining reasonable safety margins. The straight track section eliminated curve speed restrictions that would have limited maximum velocity, while the long gradient allowed sustained acceleration to terminal velocity. The test train composition reflected compromises between achieving maximum speed and generating usable publicity. 3 coaches provided sufficient weight for stability while minimizing resistance that would limit terminal velocity. The dynamometer car recorded precise speed, power output, and mechanical performance data that would validate or refute the record claim. Weather conditions on July 3, 1938 offered near-ideal circumstances. Light winds minimized aerodynamic resistance variability, while dry rails provided maximum adhesion for acceleration phases. Driver Joseph Duddington, selected for his experience with high-speed operation and steady nerve, began the descent from Grantham with Mallard in perfect mechanical condition. At Barkston, speed reached 104 miles per hour as the locomotive accelerated down the gradient. Duddington maintained full regulator opening with long valve travel settings that maximized steam admission to cylinders. Fireman Thomas Bray shoveled continuously, maintaining steam pressure at 240 pounds per square inch, despite massive steam consumption rates. Little Bytham saw speed increase to 118 miles per hour, exceeding German State Railways' 1936 record of 124.5 miles per hour. The dynamometer car instruments recorded data that confirmed speeds previously considered impossible for steam traction. Mallard's mechanical systems operated smoothly despite stresses that exceeded any previous British locomotive experience. At milepost 90, between Little Bitham and Essendine, the speedometer reached 126 miles per hour at exactly 5:27 p.m. For a brief moment, Mallard sustained velocity that represented the absolute limits of steam locomotive performance. The aerodynamic design, thermodynamic efficiency, and mechanical precision combined to achieve speed that validated 4 years of controversial engineering decisions. The middle big end bearing failure immediately following the record run provided sobering reminder of the mechanical limits involved. Sustained operation at 126 miles per hour generated bearing loads that exceeded design specifications. White metal lubricant liquefied under pressure and temperature conditions that no locomotive had previously experienced, causing damage that required immediate repair. Inspector Sam Jenkins' dynamometer car records provided indisputable evidence. The continuous speed trace, witnessed by LNER officials and independent observers, documented acceleration to 126 miles per hour and sustained operation at extreme velocity. The data contradicted any suggestion that the record resulted from instrument error or measurement uncertainty. The news reached London headquarters within hours. Railway executives who had supported Gressley's experimental program received validation that justified their faith in streamlined design. Critics who had dismissed the A4 as expensive publicity stunt faced undeniable evidence that British engineering had created the world's fastest steam locomotive. Mallard's record would stand forever. No subsequent steam locomotive would exceed 126 miles per hour despite decades of additional development. The combination of aerodynamic design, thermodynamic efficiency, and mechanical sophistication represented the ultimate achievement of steam locomotive technology, a performance level that marked both triumph and technological limit. Mallard's world record transformed industry perceptions of streamlined locomotive capabilities, but its lasting significance extended far beyond a single afternoon's achievement. The A4 class operated express services for 28 years, accumulating millions of miles in regular passenger service that demonstrated sustained reliability critics had insisted was impossible. The class's operational economics proved more impressive than the speed record. A4 locomotives consumed 12 to 15% less coal than conventional Pacifics on equivalent duties, savings that accumulated into substantial operational cost reductions over decades of service. The aerodynamic and thermodynamic improvements delivered continuous financial benefits rather than merely enabling occasional high-speed demonstrations. Post-war service revealed the design's adaptability when operational conditions changed dramatically. After 1945, the LNER faced coal rationing and lower quality fuel that challenged all steam locomotive operations. The A4's efficient steaming capacity allowed maintained schedules using inferior coal that reduced other locomotives' performance significantly. The Kyle-Chap exhaust system's superior draft characteristics proved particularly valuable when fuel quality deteriorated. The streamlined casings that critics had dismissed as maintenance complications actually protected machinery from weather and track debris. Bearing temperatures remained more stable than exposed designs, while lubrication systems operated more consistently. Maintenance intervals eventually exceeded conventional locomotives, rather than requiring more frequent attention as skeptics had predicted. Preservation of 6 A4 locomotives, including Mallard, reflected recognition that these machines represented pinnacle achievements of British engineering. Museums worldwide sought examples because the class symbolized innovation that challenged conventional wisdom and succeeded despite widespread skepticism. Modern high-speed rail development, particularly Britain's advanced passenger train and subsequent projects, studied A4 operational records extensively. The relationship between aerodynamic design and sustained high-speed performance that Gressley pioneered informed electric and diesel locomotive development decades after steam traction became obsolete. The engineering lesson transcended specific technologies. Mallard demonstrated that systematic innovation addressing multiple performance limitations simultaneously could achieve results that incremental improvements never accomplished. The combination of aerodynamics, thermodynamics, and mechanical refinement created capabilities that exceeded the sum of individual improvements. Today, Mallard resides at Britain's National Railway Museum, polished and preserved as testament to engineering vision that refused to accept conventional limitations. The streamlined profile that Victorian-era critics mocked as impractical fantasy now symbolizes British engineering's finest achievement in steam locomotive development.